My name is Yanjun Pan. Today we are going to talk about measuring ambient cellular signals in high mobility conditions. The main thing of this talk is to explore the experiment approach of our work that appears in NDSS 2022, titled Proof of Following, POF, Proof of Following for Vehicle Platoons. This talk will start with presenting our initial research hypothesis. Then we will describe the rest experiment designed to test our hypothesis in different settings, as well as the RF and platooning testbed. Finally, I will share the challenges and useful experience we obtained from this work. So the most important feature of platoon is the dynamic formation. That is, consider the two vehicle platoon just as shown in this figure. The verifier should be able to let the candidate join to the platoon when the request is sent, and once verified, this candidate should be able to inject his own messages into the platoon head and have some control over the whole system. Traditionally, this is done with digital signatures built upon public key cryptography. However, in this way, we can only verify the digital identity of the candidate. There is no way for us to verify the candidate's physical properties in the existing protocols. So in conclusion, the crypto itself is not sufficient to verify the candidate's physical properties such as its location, proximity, time, speed, and so on. But it is very important for us to verify the candidate's physical properties to secure the platoon system. To this end, we propose the concept of proof of following. That is, for a given route of V and C, the distance between V and C should be bounded with the set reference distance derive at any time of the route. In this way, we can have the physical access control of the platoon so that only platooning members who are really following the platoon can communicate with each other and have control over the system. To do that, our main idea is to exploit common dynamic contexts, and this is based on the simple hypothesis. That is, for two vehicles which are drive closely, they should be able to observe the same environment. The most important feature for such common context is that it must be dynamic in terms of spatial and temporal domain. That means such contexts need to change during the driving, and it should also change over the time. In our work, we use RF modality. More specifically, we use large-scale RSS. The hypothesis behind this chosen modality is that for two vehicles which are drive closely, they can observe the same large-scale RSS received from the critical infrastructure, such as LTE tower. So in this way, we can have the simplified POF protocol. That is, first, the candidate sends a request to the verifier to join the platoon, and the verifier will verify the digital identity of the candidate by using the encrypted message as well as its digital signature and certificate. After that, the verifier sends a synchronization signal to the candidate to tell its the timing information for the RSS connection. With the timing information, both the candidate and verifier will collect the RSS. After that, the candidate sends the collected RSS to the verifier, such that the verifier can compute the RSS correlation and further make the decision built upon it. So the decision will be either accept the candidate or reject it. The main hypothesis we use to design our protocol is that the spatial correlation of the two vehicles V and C will decrease with distance. And the left figure shows this relationship, where the y-axis is the correlation coefficient of the RSS received by V and C, and the x-axis is the distance between those two vehicles, which is normalized with the decorrelation distance, depending on the environment. And this figure shows that such correlation coefficient has an exponential decrease relationship with the distance between those two vehicles. Besides, such correlation will also decrease with time, and we can collect those RSS features with in-band modality using existing receivers, such that no extra hardware is needed. To verify our hypothesis, we need to measure the RSS correlation from two aspects. The first is that we need to verify that we need to control the distance between two moving vehicles so as to validate the spatial correlation relationship. At the same time, we also want to know the temporal correlation with the time, so we need to control the time at the same location in order to compute such temporal correlation. There are several challenges in terms of the data collection and the data analysis. First, let's look at the main challenges that we encountered with the data collection. First, we need to select the LTE band for the ambient RSS sampling, because those two vehicles, the verifier and the candidate, only need to listen to the signals received from the LTE toler, so that we need to select the correct LTE band. Besides, just as we mentioned, in order to compute the spatial correlation, we need to control the distance between the moving vehicles in realistic conditions. Also, for the data processing purpose, we also need to have the geotag and timestamp of our RSS samples. Finally, for the evaluation purpose, we need to run the experiment multiple times in various settings to collect sufficient data, and also show that our approach is general in terms of different environments. First, in order to get the geotagging and the time samples with RSS samples, we first try to use the onboard modules of an Android phone. Our original idea is that we can use the LTE receiver on the Android phone to record RSS, since there are some apps that directly provide such information. Besides, we can use the GPS on phone to get the geotag, as well as use the internal time clock to record the timestamp. However, it turns out that this approach doesn't work because we could not control the LTE channel recorded by different phones. That is, for different phones, we cannot manually set them to listen to the same LTE channel. Besides, the onboard modules on the Android phone has low GPS sampling rate relative to the RSS sampling rate, and we also have low resolution timestamp. In order to solve those issues, we switched to a proof of concept USRP testbed. Here we show our hardware layout, where we have the laptop that control all our hardwares, and the RF signals are received with USRP, which is powered by the power supply. Also, to get the geotag information, we have the GPS, which is controlled with the phone. Just as we said, the first challenge is to select correct LTE band. In fact, we observed that with the specifications of the antenna and USRP we use, there are multiple LTE bands that can be used. More specifically, there are 8 LTE bands that we can use as listed here. So our problem goes to select the correct one in those candidates. And our goal is to select bands with the highest average RSS. To this end, for this given route, we drive the car on this route with each band. And for each band, we will compute its average RSS and select the band with the highest RSS. After that, we narrow our sampling band in order to get more strong data. And according to our result, for the urban setting, we select the band as 1.972 GHz, and we use band 875 MHz on highway and freeway. And for our data processing and recording, the bandwidth we use is 4 MHz. Our next challenge is to control the distance of the moving car. To that end, first, we decide the initial distance between those two cars with roadside markers. After that, we count down with phone calls and then start the car. Also, we mentioned that we need to have the geotag information, and we verify the average distance between those two cars with GPS data. Such kind of the experiments has been repeated for different following distance. Next, we mentioned that we use the GPS to get the geotag information as well as the timing step for the RSS samples. So first, the RSS time steps are generated by the laptop connected to each USRP. First, we synchronize the time step on those two laptops, since those two laptops will provide the time step for our USRP. And then for each RSS sample we collected, we give it the time step read from the laptop. So here, those two tables shows the RSS value as well as its corresponding time step for those two USRPs correspond to our candidate and verifier, where the left column shows our RSS in dBm, and the right column shows the time step read from the laptop. Next, let's look at the geotag information. Also, we collected the geotag as well as the time step of those two cars from the two GPS devices. And similarly, in those two figures, we show the time step as well as the geotag we collected from the GPS. So from the time steps of the RSS samples as well as the GPS information, then we can get the location of the car at a specific time with the corresponding RSS value. With all those set up, now we can validate our hypothesis. First, we focus on validating that the spatial correlation between those two cars will decrease with the distance. To this end, just as we mentioned, we control the distance between those two moving cars. So here, the falling distance of those two cars is shown in the x-axis. And in this figure, the y-axis shows the computed correlation. And we want to mention that for those 2 points, which has a very small falling distance, in these cases, we put the two USRPs representing candidate and verifier into the same vehicle. And from our experiment result, we can see that the spatial correlation does decrease with distance, just as we expected. Next, we verify our hypothesis that the temporal correlation also decreases with time. So here, for those two figures, the x-axis is the time difference. for the same route under different time, and the y-axis is the computed correlation. For the left figure, we show the correlation relationship in terms of the time with units second, and for the right figure, we observe it in a large-scale time, where this time is represented in minutes. For both of those figures, we can see that we do have the decorrelationship with time. So our preliminary experiment results did validate our hypothesis. Then let's look at our platooning testbed on urban environment. For urban environment, we select a route with distance 2.5 miles inside Tucson, and we set the reference distance between those two cars as 11 meters on average, and we drive those two cars at a speed of 14 miles per hour. And here we shows the relationship of the distance between those two cars as different driving time, where we can see that the distance between those two cars is quite stable for most of the time. Next, for the highway, we use different settings where the verifier is controlled with cruise control, and the candidate will follow the verifier on an adaptive cruise control. In other words, for our highway experiment, we did use platoon. And the route we selected for the highway is a 8.5-mile route on I-10 highway. Here also let's look at the distance control with our setup. This right figure shows the relationship between those two cars over different driving time, where we can see that at the speed of 55 to 16 miles per hour, with our setup, we do have the stable distance of 53.4 meters between those two cars. And also for our bottom figure, we show the car we use for our candidate, and also those RF testbed is put in it. Just now we mentioned that it is very important for us to measure the physical properties of the candidate to secure the platoon system. Let's look at our stress model to see why that is necessary. In fact, the adversary can inject the request to the platoon system through any kinds of the critical infrastructure. First, we can have the pre-recording attack, where we have the remote adversary who obtains the RSS on the exact route ahead of time. Then, at the time when the adversary needs to attack the system, the adversary just injects the pre-recorded RSS data into the verifier. Besides, we can also have fully real-time. We can also have far-away adversary who is following the platoon in real time, but at a distance which is much larger than the reference distance. So, for performance evaluation, we would like to verify the performance of those two adversaries in different settings. First, we verify the performance of the adversary in urban experiment. And for the remote adversary, or seeing the pre-record adversary we mentioned, we use one vehicle, drive on the exact route, and pre-record the RSS 70 minutes ahead of time. And for the following of our adversary, we use one vehicle which works as the adversary to follow the verifier at an average distance of 125 meters. Especially for the following of our adversary, we use the bottom figure to show the relationship between the distance of the verifier and the attacker over different time. Here we can see that the distance between those two cars is not that stable compared to the distance between the verifier and the candidate because of the traffic. Similarly, for the highway experiment, we also validate those two types of the adversaries. And for the remote adversary, the vehicle was drive on the exact route and pre-record the RSS 40 minutes ahead of time. While for the following of our adversary, the attacker is following the verifier at a following distance of 250 on average. Similarly, the distance between the attacker and the verifier over time is not that stable because of the traffic. Next, we go to our data processing. In fact, there are many factors that are involved in our POF protocol, and we need to find a uniform algorithm to design those parameters. First, let's look at any kind of the RSS collection. Seeing that, let's look at the RSS collected by the verifier, denoted as gamma v from time 1 to time I. First, we will group this dataset into k groups, and each group will have n samples. Here, this k will be the total number of our test, which means only when the candidate pass a portion of alpha total tests, it will be accepted. With this partition, we will have k groups of the collected RSS sample. And then for each RSS sample, in order to get the large-scale RSS, we need to filter out the small-scale fitting. To this end, we apply an endpoint moving average to get the large-scale RSS. With the smooth subset, we can compute the correlation between the RSS collected by the verifier and the candidate. Let's denote this correlation as rho, and for each test, if this rho is greater than a given threshold, then we see a single test is passed. And just as we mentioned in our protocol, we will use multi-test, seeing that for a total number of k tests, only when the candidate has alpha times k number of tests, it will be accepted. Otherwise, we will reject the candidate. Our first issue is about selecting those parameters. First, let's look at how we select the parameter n and m, which represents number of the samples in each subset and the moving average window size, respectively. To decide those two parameters, we use the same data obtained from the hypothesis validation. And for those two figures, we show the relationship between the correlation coefficient and the following distance under different selection of n and m, where the y-axis is the correlation and the x-axis is the following distance. For those two figures, we can see that with the increase of n and m, such correlation will increase. However, the benefits will eventually diminish. So to balance the overhead of computing and the performance, we select N as 400 and M as 20 for all our following analysis. Besides, I want to mention that those two figures also validate our hypothesis between the spatial correlation of the distance. Then our next problem is about the other two parameter selection, seeing that the number of the total multitest K and also the threshold for the correlation tau, as well as the portion of the multitest the candidates need to pass, which is related to the parameter alpha. To select those two parameters, we need to introduce a new metric, which is called equal error rate. First, let's look at the property for any given vehicle to pass at least X number of the tests. For example, for the candidate, we denote such accumulated property as f of k, big F of k, which is equal to the binomial trio tests. Then, with the number of the equal error rate, which means the number of the candidate to fail the multitest equal to the probability of the adversary to pass the test will equal. Then, in this case, first we decide a total number of k, and then compute the equal error rate. To have the equal error rate, we will only have one specific solution for the given k and tau. And the right figure shows such result, where the y-axis is the computed equal error rate, and the x-axis is the number of the multitests. And for each line, we use a specific tau. In such figure, we can compute the minimum equal error rate, which gives us a k that will produce the best performance of our protocol. Just now we mentioned how we select the number of the total test k. Then with this k, let's see how we can decide the threshold tau as well as the portion alpha. First, it is very intuitive that the probability for the vehicle to pass a single test will decrease with the threshold tau, and the first figure shows the relationship where the y-axis is the passing rate for a vehicle under a single test, and the x-axis is the threshold tau. And then with this threshold tau according to our equal error rate, where we can find the minimal equal error rate, as well as getting the corresponding alpha and k, we show those values in the last two figures, where we can see that with those two figures, we will have a minimum setting that will give us the minimum equal error rate and the corresponding tau and alpha as well as k. So this is the way we select k, tau, and alpha. And we want to mention that those parameters can be updated in real time, where the verifier can ask the vehicle ahead of it to send the data to it in order to update such parameters. Then with those parameters, we can evaluate our protocol performance. First, we show the experiment results in urban environment under the pre-recording attack as well as falling of our adversary. For those two types of the adversary, from these figures, we can see that the passing rate for the adversary goes to 0 when we increase the number of the multitests, while the passing rate for the candidate will goes to 1. Similarly, we validate our protocol performance on the highway where the distance between those two vehicles is set to 53 meters on average, just as we mentioned, and those two cars are driving at the speed of 16 miles per hour. Similar to the results in urban environment, we can see that for the passing rate of the candidate, it will go to 1 when we increase the number of the multitests, while such rate for adversary will go to 0 eventually. So that's all for our the implementation of this work. And here are the lessons we learned. First, for the off-the-shelf equipment, to get accurate geotagging and timestamp for RF samples can be really challenging in practice. Besides, the data collection in realistic driving conditions is also a tedious process, since the equipment would not always record reliably, and it can involve many experiments to have the correct setting. Besides, maintaining the constant distance between vehicles without adaptive cruise control can also be very difficult. Moreover, the surrounding traffic can harden controlling the experiment parameters. Furthermore, we know that testing the main hypothesis was crucial for further developing the method, and the collection of the large dataset can allow us for fine-tuning on test parameters, where the data was processed and analyzed in different ways to give us the best selection of the parameters.